Good afternoon. I'm Cristiana Tarantino from the Department of Structures for Engineering and Architecture at University of Naples, Federico II. And today I'm going to present you this interesting case study about a monumental building sited in Maiori on the Amalfi Coast, exposed to multiple natural hazards and characterized by several instabilities. The subject of this study is the Convent of San Domenico, a 17th century masonry building. Its importance is related first to its cultural and historical interest. Indeed, it is one of the few surviving elements of the historical urban fabric of Maiori. It contains interesting details of Baroque architecture and remarkable artistic works, such as a fresco by the local painter Gaetano Capone. And furthermore, very few buildings along the coast can compete with its dimensions, whereby it represents an important special resource for the city and the entire coastal area. Here are some few images showing the state of conservation of the building. It was abandoned since the 80s when a strong earthquake produced severe damage and it has never been restored. Our interest in this architecture was initially related to its exposure to multiple natural hazards. As a matter of fact, the convent is exposed to high landslide risks, to floods, and to earthquakes. For this reason, the building has been included as a case study within the framework of the research project Pericles, funded by the Italian Ministry of Education and aimed to develop sustainable strategies for the protection of the cultural heritage threatened by natural hazards. This work is part of the study conducted within the research project. So the object of the study is to identify the most probable causes of the ongoing instabilities among the multiple natural phenomena that threaten the building. We did it applying a multidisciplinary approach to study the building and the foundation side, trying then to interpret the damage through the comparison between the crack pattern detected and the results of the numerical analysis. The Convent of San Domenico is located in Maiori, a small town of the Amalfi Coast in the province of Salerno, Campania region, and it is a UNESCO site well known all around the world, inscribed in the World Heritage List since 1997. The building is located in the innermost part of the town on a flat area located in the immediate vicinity of the River Regina, the watercourse that crosses the whole town and which certainly affects the mechanical characteristic of the foundation soil. Looking now at the architecture, the convent is a porticoed courtyard building characterized by a complex plan configuration, which is the consequence of several manipulations and adaptations carried out during the centuries. It is composed by 4 bodies of different width and height, placed around a square courtyard of 32 side length meters. And 2 of them, the east and the north blocks, develop for 2 levels, while the last 2 feature a single above ground level and only consist of a portico covered by a panoramic terrace facing the sea. At the ground floor, big barrel vaulted halls open off, while the south and west porticos have blind back walls. On the first floor, a long corridor runs the whole building and serves all the rooms, once being the monk's cell. The vertical connection was once granted by 2 stairways, but today only the one on the east side is serviceable. The whole structure is in masonry. The thickness of the masonry walls ranges between 120 centimeters at the ground floor and 60 centimeters on the last level. The horizontal structures instead consist of a great variety of vaulted structures made of yellow tuff. Groin walls span along the portico and the corridor at the first floor. Big barrel vaults cover the rooms at the ground floor, while cloister walls roof the sequence of monastery cells at the first floor. The roof is made by double sloped timber structure covered by clay Roman-style tiles. Some detailed information about the foundation structures was made available by a geognostic study carried out in the 1987. The foundations are dishomogeneous and placed on different laying surfaces, that's what we know, and we can find superficial continuous masonry foundations, deep masonry foundations of pillars connected by arches, and deep masonry foundations of pillars connected instead by walls. Let me give you now a few historical informations. The construction of the building started in 1650 and it was long and complicated due to several structural instabilities caused by the poor quality of the foundation soils. In the 1809, after the suppression of the religious orders, the convent was abandoned and left without any use for about 50 years. In 1865, the local authorities acquired the whole building and settled inside three different functions: a courthouse, a jail, and a school. In some rooms of the building instead were already legally occupied as houses by the locals. Consequently, very invasive restoration work were carried out to adapt the old construction to the new functions. Lofts were created at the ground floors and new windows were opened in the bearing walls. At the first floor, large arched openings were created in the transverse walls to define the classrooms, enlarging the old monks' cells. In 1980, a strong earthquake heavily damaged the structures and the building was definitely closed and abandoned. In 1985, a new project of restoration was launched, but it was not completed due to the lack of funds. So nowadays, the building is still closed, abandoned, and in critical condition. In fact, it currently presents an extensive and diffuse crack pattern that is the consequence of several causes, such as the natural aging of material, the lack of maintenance, the modifications occurred during the century, the seismic events occurred in the past, and possible mechanisms related to the poor quality of the foundation soil. The crack pattern increases in intensity and extent from the ground upwards. The groin walls of the portico and of the corridor at the first floor show cracks in the center line at the attachment to the wall, corresponding to the typical three-hinged mechanism. The door vault of the monk's cells exhibit diagonal cracks and multiple dense cracks parallel to the curtside wall. As for the east wing, a different crack pattern is observed, which differs from the one observed in the rest of the building. In fact, the big barrel vaults of the ground floor walls are completely detached from the head wall, separating them from the court. At the first floor, the door vaults of the monk's cells on the court side show a more complex and braided crack pattern. In parabolic fissures develop on the transverse walls and some cracks open out on the floors. A partial collapse of the roof can be observed at the middle length of the block, not referable to a break of the timber structure, which still appears in good conditions. Moreover, the presence of subvertical cracks on the foundation arches in the southeast corner is reported by the geognostic study from the 1987. So the interpretation of the crack pattern in this area of the building is not straightforward, as it seems to be the result of different phenomena that acted on the building together. That's why a numerical model of a cross-section of this wing has been developed and analyzed under two different conditions: lateral loads and settlements. The structural analyses were carried out using LIA-Block 3D, an in-house software tool for the limit equilibrium analysis of masonry structures, modeled as an assemblage of three-dimensional blocky structures, which provides as output the most vulnerable collapse mechanism for a given loading condition. The software is based on a point contact formulation and implements the lower bound problem of limit analysis. The numerical model is an assemblage of rigid bodies interacting one another through no tension friction contacts characterized by infinite compressive strength. The model of the east wing was developed considering a characteristic transverse section, which is representative of the whole wing, considering the modularity of this part of the convent. The section is obtaining correspondence of the symmetry plane between two consecutive spans of the portico and includes the most relevant structural elements of the wing. To solve some modeling issues deriving from the gap between the two-dimensional model and the three-dimensional conception of the construction, special components were created. It is the case of the sub-arch of the ground floor barrel vault, which develops in the orthogonal direction of the plane considered in the analysis. A support block has been introduced in its place to sustain the left wall of the first floor corridor. The model is composed by an assemblage of 685 rigid blocks. The discretization of the structure in rigid blocks does not reproduce exactly the real masonry texture, but was defined so as to reproduce the average size of the real stones. A refined discretization was adopted instead along the arches to enable the freeze formation of the hinges required by the collapse mechanisms associated to the imposed actions. And additional data were required by the software LIABlock for the analysis, and they are related to the material properties. So the weight per unit volume of the masonry was assumed equal to 21 kilonewton per cubic meter, and the value of the friction coefficient was set equal to 0.6. The numerical analysis for lateral loads have been carried out by applying a set of lateral forces applied to the centroid of each rigid block, acting along the x direction in two opposite directions. The figures show the collapse mechanisms corresponding to the non-associative solution of the two in-plane seismic analysis in the positive and negative x direction, respectively. When the load acts in the x-positive direction, the collapse condition occurs for a low value of the load factor, as you can see in the table. The overturning of the curtailed facade is activated, and as a consequence, a typical 3-inch mechanism develops in both the round and the low arches of the right span of the section. The mechanism also causes the sliding of the timber beam and thus the roof collapse. When the load acts in the x-negative direction instead, the load factor needed for the collapse is higher. The left and the middle spans of the section almost behave as a unique block, overturning and causing the serious damage visible in the right span of the section. The global damage of the seismic in-plane analysis is partly compatible with the surveyed crack pattern, as it was expected since no restoration works have been done after the earthquakes, but it contemplates a slight damage of the innermost structures of the section and doesn't detect the floor cracks at the first level. So we went on with the settlement. On the base of the localization of the cracks and the damage traceable to a potential soil failure, two different schemes of ground vertical displacement were implemented. The first one considers a uniform vertical displacement imposed at the base of the portico's pillar in point A. The second examines the case of the same movement imposed at the base of the portico's back wall in point B. Looking at the first settlement scheme, the failure involves only the first span of the section on the portico side. The collapse occurs with a 3-inch mechanism in the ground floor arch and a 2-inch mechanism in the low arches at the first floor. The overturning of the portico's pillar and the sliding of the roof's beam are also consequently triggered. Observing instead the second settlement scheme, we can see that the damage affects the whole structure. The collapse still occurs with a 3-inch mechanism in the round arches of the portico and of the upper floor corridor, while a 2-inch failure mode develops in the low arch of the transverse wall. This again results in the overturning of the portico's pillar and the sliding of the roof's beam onto the first span of the section. The mechanism slightly affects also the last span of the section due to the possible little movement provoked in the barrel vault. Between the two collapse mechanisms predicted by the numerical model, the second one, corresponding to the B settlement scheme, is in good agreement with the surveyed crack pattern. As we can see, looking at the section here represented and reporting the damage survey, the mechanism catches almost all the existing cracks. At the ground floor, the barrel vault detachment from the head wall on the portico side in lesion A, and the cracks in the covering structures of the portico in lesion B, and also at the first floor, the cracks in the vaults and the arches of the corridor, at the floor, in the transverse walls of the right room, and the failure of the roof too. So to conclude, the damage analysis of the Convent of San Domenico has been presented. We adopted a multidisciplinary approach to study the building from a historical, structural, and architectural point of view. We derived some information from a geognostic study, and we did an accurate geometric and damage survey. On the basis of these information and data, we identified the most probable causes of the ongoing instabilities, and we verified them by using the software LIABlock 3D. We made two types of analysis, one for lateral loads and one for settlements, and the results of the analysis are in good agreement with the crack pattern detected and provides new important elements to identify the causes of the instabilities. Further development of the study will address more in details the interaction between the structure and the soil, and will also extend the analysis to a full 3D model. Thank you for your attention.